Next, 6.90. We wish to explore various reactor setups for transformation of A into R. The feed contains 99% of A and 1% of R. Desired product consists of 10% of A and 90% of R. So feed is 99% of A and only 1% of R. Desired product is 90% R, only 10% of A. The transformation takes place by means of elementary reaction, A plus R giving you R plus R. So autocatalytic reaction. With the rate constant K as 1, the concentration of the reactive material is Ca0 plus Cb0 is equal to Ca plus Cb, which will be same as C0 in its total initial concentration, 1 moles of per liter. What reactor holding time will yield a product in which Cr is equal to 0.9? You want this 90% means 0.9 moles per liter. First part in plug flow reactor, then in mixed flow reactor, and then C part minimum size setup without recycle. So combination of mixed flow, plug flow, whatever combination is best, you can see. So here Cr0 plus Ca0 is Ca plus Cr is C0, that is 1, that we know. Minus Ra is K is given as 1, so 1 into CaCr. Cr is 1 minus A, so Ca is Ca into 1 minus A, minus Ra value. Here Ca0 is 0.99, that is given, so this we have substituted here. C0 is 1, Ca 0.1. So Ca 0.1, C0 is 1 and Ca0 is 0.99, all substituted. Ca0 plus Cr0 is 1. Okay, so this is 1. K is also 1. So this calculated value will be directly tau p. So tau p is 6.7923 minutes. Tau p value. Tau m, if you want to calculate for mixed flow reactor, it will be C0 minus Ca by minus Ra. And you start with this Ca0 value. This is the model equation. So we start with this value and Ca0. Same thing we are doing now in mixed flow reactor. So you start with this value Ca0. This is Ca. Ca 1 minus Ca. So this comes out to be 9.889 minutes. So if you carry out the reaction in plug flow reactor, tau p will be 6.7923. So holding times you have to calculate. In mixed flow, it will be 9.889. Final Ca desired, you know, it is 10%. So that means 0.1. And you start with 99% of it. That means 0.99. Now we look at this data. Ca and Cr. We start from Ca is equal to 0.99 and end with Ca is equal to 0.1. This total is 1. So Cr just found by difference. So initially there is Cr and that is 1%. So it is 0.01 moles per liter. And you can calculate just by difference. And finally Ca leaving is 0.1. So Cr will be 0.9. Total is anywhere it should be 1. That is C0. Minus Ra is K CaCr. So you know CA, you know CR, K is 1, these values are calculated. 1 upon minus RA, just invert it. And now make a plot of 1 upon minus RA versus CA. Okay. And we start here 0.99 and finally 0.1. This is 0 and this is 0.2. In between we have 0.1. Okay. This is the curve. This is the curve. So we have calculated by using the equations. Same thing. Tau P will be area under the curve for same performance. So if you find out, count these rectangles and area under the curve carefully, then you will get exactly same result almost as 6.79. So some plus minus error will be there. For tau m with respect to this exit concentration. So area of this rectangle, that you will get. This value of 1 upon minus RA 11.11. So graphically also you will get same. Now what we want to do is, why we have plotted this, not just to check this, but we want to find out again some intermediate concentration here and suggest a scheme of two reactors. So you can see here I have taken this point at 0.5 somewhere. This you have to set by trial and error again. So 0.5, few values you can try, and this area under the curve plug flow, and this is mix flow, this small rectangle here. So if you measure, count the number of squares and multiply by area of one square, you will get these values: 2.197 minutes tau p and 1.96 minutes tau m. So total for this, if you go for this setup, instead of going for a single PFR or single MFR it is highest, then single PFR, and then if you use this combination tau p plus tau m is only 4.157. So this gives you the best result. So 2.197 and 1.96 you can find this from area under the curve and this from the area of the rectangle, and this we have calculated point identified 0.5. So you can calculate it from the model equation also. So this is 0.5. So 0.5 into 1 minus 0.1, 0.1, 1 minus 0.5 tau p. So your plug flow reactor starts from this 0.5 to 0.1. So this area you can find out, and exactly same result you will get here. Tau m, your mixed flow reactor is from 0.99 to 0.5. So you can see here 0.99 to 0.5, and that is 1.96. So this scheme is best. Now how to locate this point? This we have seen for 0.5. Now you can take some points here and see this. This is the smallest possible rectangle for mixed flow, and similarly this area is also very. So in this area, one or two tries will give you the best possible result. Here the maximization of rectangle that we have seen, as this is a flat curve here in this area, so you have to find out only by eye judgment. Okay, so drawing the tangent, and here you can try that also, and this is not, there is no guarantee that this is the best solution. You may have best point somewhere else. There may be more than one best points that we have already seen. So you have to use your judgment, some trial and error, and find out the best situation, that is total volume should be minimum. Maximization of rectangles we have applied where we have used mixed flow reactors in series only. Okay, because for both the cases you will have two rectangles, and remaining rectangle we want to maximize so as to minimize the total area of the two rectangles when two mixed flow reactors are in series. Here there is one plug flow and one mixed flow, so that method will not work correctly here. So we have only one option to go for trial and